Hello, my name is Boris Platov, and this is Center for Advanced Training, Quality Management and Marketing, Institute of Geology and Petroleum Technologies, Kazan Federal University. And today we are going to talk about seismic interpretation. The first successful seismic works was carried out in the United States in 1924. In the Soviet Union, the first successful work was carried in the early 30s. So, what is seismic? Actually, seismic exploration consists of several steps, which is going one by one. The first is planning, then the field work, and then it's going to be the field processing, and then it's go to detailed processing of the initial seismic data. And after detailed processing, there are the actual step of seismic interpretation. And to fully understand the seismic interpretation step, we have to keep in mind that there was quite a lot of steps before that. But right now we are going to talk only about seismic interpretation. And to simplify the case, we're going to talk on how these seismic waves are occurring. First of all, we got a kind of a seismic vessel. It can be either on sea or on land. We are using a certain source of the seismic waves. Usually it's a bomb or any other source of seismic waves. So we shoot the wave, it's going down, reflects on a certain surface, and then going up to reach our geophone or hydrophone, reach our receiver. And this time on the receiver we obtain a certain signal, certain amplitude. Then another wave is traveling from the source to a deeper horizon, reflects, and going up to hit the same geophone. And we obtain the second reflection, and so on. During the recording of the seismic reflections, we can record quite a lot of this type of reflection, of this type of oscillations. And we receive the same seismogram in all of the receivers. And then if we simply align them together along a single profile and simply color the positive amplitude in black and the negative amplitude we leave just white, we're gonna obtain this kind of picture. On this picture we can see quite a lot of different seismic traces along each picket in our seismic profile. And that is the seismic image. If we look deeply on the seismic image, we can find out that, for example, here we got a huge positive amplitude colored with black. And on the next point we got the same. And on the next point we got the same big positive amplitude. And here we can start thinking that all of these positive amplitudes actually came from the same object below the surface, which reflects all of our waves. And in geological exploration, we start thinking that that's what the boundary between the layers. Another type of coloring of that picture is to color the positive amplitude in red and the negative amplitude in blue, and the zero crossing leave the white, as shown on that picture. So you can see the big positive amplitude is red, the negative amplitude is blue, and the zero crossing is white. If you look carefully on that picture, you can find out that it's the same data spot, just a different type of visualization. The next question is the types of boundaries that are used in seismic exploration. We do have three different types of boundaries. It's stratigraphical boundaries, lithological boundaries, and physical boundaries. If we're talking about stratigraphical boundaries, that's the boundaries of the age, between the rocks of different age. like between Devonian and Carboniferous, between Carboniferous and Permian, and so on. The next step is lithological boundaries. It's simply a change in lithological properties like sandstone to shale, shale to limestone, limestone to dolomite, and so on. And the last type of boundaries is physical boundaries. That's the change in physical properties. In our case, in case of the seismic, the physical property usually corresponds to acoustic impedance. Acoustic impedance is the multiplication of the density and velocity of the layer. And reflection occurs according to that equation. That's the equation for calculating the reflection coefficient. Acoustic impedance of the second layer minus acoustic impedance of the first layer divided by stack of these two acoustic impedances. What does this equation mean? It means that once the wave is going down, hits the boundary, it can be reflected, and the amount of the energy that would be reflected can be calculated according to that equation. And that simply means that once we get a boundary on which we get a strong change in density and velocity, we're going to have a big reflection. And vice versa. If on the certain boundary density and velocity is not changing dramatically, we're going to have a small reflection, a weak reflection. Let's talk about dimensions in the seismic data. Let's talk about dimensions in the seismic data. The first thing is 1D data. 1D data is the check shots or the vertical seismic profiling. In this case, we have well drilled with a certain seismic receivers installed down the hole. We are shooting a bomb on the surface, and the wave is traveling from the surface down to the seismic receiver in the well. In this case, we know the depth of this receiver from the well. We know the time of seismic waves took to reach this point, and we can calculate velocity. 2D seismic. In this case, we are using two different coordinates. The first is a number of piquet along the seismic profile, and the second one is time, which is going down here. And for each point, we get the value of seismic amplitude. 3D seismic cube. In this case, we got three coordinates, x, y, and z. And for each of these three coordinates, we can obtain the value of reflection, the value of amplitude. In addition to that, we could have the 4D seismic. In 4D seismic, we are shooting the same 3D shots in a different time. For example, in this case, in this picture, we can see the first shot in 1992 and the second shot in 2003. And we can see that the reflection of the horizon was changed dramatically. And this change actually occurs because of the change in the saturation. In 1992, we got all of the layers saturated with gas, and 11 years after, we see that gas leaves only in a certain point. That means we can monitor the process of the excavation of reserves using 4D seismic. There are two main types of interpretation: kinematic and dynamic. Kinematic interpretation. It gives us information about geometry of the seismic lines. For example, we can trace a certain horizon and find out its geometry, whether it's uplifted or vice versa. In case of dynamic interpretation, we are talking about a bit different things. For example, here we can see a huge amplitude, and right nearby we can see a small amplitude. So we can find out that along a single horizon we do have a dramatic change. Along a single horizon we do have a dramatic change in the amplitude, and that corresponds to the change in the properties of the layer. And this change in the properties we can find out using dynamic interpretation. What for do we need to do seismic interpretation? In our case, in case of an oil and gas industry, we are looking for a reservoir which contains oil. That means we are looking for the oil trap. And trap is a part of the natural reservoir that can collect and hold hydrocarbons. There are several types of oil traps. The first type is anticlinal trap. In this case, we have a certain band in the reservoir layer covered by a certain seal, like the cap rock. In this anticline, we can collect a huge amount of oil and gas. In the seismic data, it looks like it's shown on that picture. So the uplifting of the reflection and then down, it falls down. There are certain types of non-anticlinal traps. Let's talk a bit about non-anticlinal traps. The first is salt dome. Salt is a mineral that is actually solid, but under a huge pressure and temperature, it can start do the behavior as a liquid, and it tries to move up to the surface. In this case, it can cut the upper layers along its way, and in this case we can find out the presence of the new oil traps, which do not belong to an anticline, but it is coated by the salt dome. Another possibility is the change in the thickness. For example, here we can see the huge thickness between two layers, which is going down, and the two layers actually touch each other. In this case, we can also have an oil trap. Another possibility is the presence of the paleochannels. For example, here we can see the huge increasing in the thickness in the distance between the upper layer and the bottom layer. In this area, we can find out the presence of the paleochannel. And that's how it looks like in a map view. So you can easily see this channel-like body. Another type of oil traps connected with the carbonate rocks. In our case, we can find out that most of the carbonate rocks actually of organic origin. So that means they all was living organisms. For example, this sample of the reef that I'm holding contains quite a lot of pore space, and its permeability gonna be high as well, because we can see this that in this pore space that this pore space actually aligned along a certain ways inside the sample. That means reefs can be good reservoir to hold oil and gas, and still it's a living organism. So in our case, it is formed not according to the actual sedimentological cycles. Reefs are growing, and they are growing only in case where the conditions is good enough for them to grow. And the reefs do not have a structured internal structure, so it don't have layers inside. For that reason, in the seismic record, we can see them as the chaotic record. For example, on that picture, we can see that here we do have a good layering, and on this area we can see a chaotic structure of the seismic record, and this corresponds to the reef.